In this video, we consider a vertically oscillating spring and derive the differential equation that describes such a harmonic spring oscillation. For this purpose, a sphere is attached to a vertically oriented spring. The sphere is displaced from its rest position and then released. The sphere now oscillates periodically around its equilibrium position. The motion occurs between a lower and an upper turning point. At these points of maximum displacement, the direction of motion reverses. In the absence of friction, these turning points are reached repeatedly. The sphere continuously passes through the equilibrium position where its velocity is at its maximum. Let us now examine the process from a kinetic point of view. The mass of the spring is neglected in comparison with the mass of the sphere. Initially, the sphere is completely at rest in its equilibrium position. At this point, the downward acting gravitational force on the sphere is exactly equal to the upward acting spring force. Next, the body is displaced downward by a certain amount. As a result of this displacement, the spring is maximally stretched and the spring force increases to its maximum value. The upward directed spring force now exceeds the downward gravitational force of the sphere. As a result, a net force acts upward on the sphere. This resultant force corresponds to the restoring force, which drives the sphere back toward the rest position opposite to the direction of displacement. If we now release the body, this restoring force causes the sphere to accelerate opposite to the direction of displacement toward its equilibrium position. Due to the continuously acting restoring force and the associated acceleration, the sphere gains speed as it moves toward the rest position. As the displacement decreases, the spring force also decreases, with the gravitational force of the sphere remaining constant. This results in a decrease of the restoring force. As the sphere approaches the rest position, its acceleration becomes smaller. Thus, the acceleration decreases while the velocity continues to increase, although at a slower rate due to the reduced acceleration. At the equilibrium position, the spring force once again equals the gravitational force of the sphere, and no resultant force acts. The sphere is no longer accelerated and therefore reaches its maximum velocity at the static equilibrium position. It moves upward through the rest position. Above the static equilibrium position, the spring force becomes smaller than the gravitational force because the spring is less stretched. A resultant force now acts downward, serving as the restoring force that drives the sphere back toward the equilibrium position, opposite to the direction of displacement. A decelerating restoring force thus arises, and as the spring force continues to decrease, the magnitude of the restoring force increases. Finally, the sphere comes to rest at the upper turning point, where the spring is minimally stretched. In this state, the upward-directed spring force is at its minimum, and the downward-directed restoring force is at its maximum. This maximum restoring force accelerates the sphere downward again, increasing its velocity as it moves toward the equilibrium position. Upon reaching equilibrium, the sphere has once again reached its maximum velocity. The restoring force, acting opposite to the displacement, then slows the sphere down again. At the lower turning point, the initial state is reached, and the process repeats itself. We can now see that the vertical spring oscillation differs fundamentally from the horizontally oscillating spring pendulum. In contrast to the horizontal spring pendulum, in which the restoring force results solely from the spring force, the restoring force of the vertical spring pendulum arises from the difference between the gravitational force and the spring force. Therefore, it is possible that the motion of the vertical spring oscillation follows a different law than that of the horizontal spring pendulum. Only the differential equation of the vertical spring pendulum can provide certainty, because it allows us to test a possible displacement function. Therefore, we now derive the corresponding differential equation for the motion of the vertical spring oscillation. This is done, as usual, by applying a force approach from which, using the fundamental law of mechanics, the acceleration can be determined. The acceleration is directly linked to the second time derivative of the displacement function. Let us first consider the spring in its unstressed state, meaning without an attached sphere. When the sphere is attached, the spring extends by a distance s0, resulting in a static equilibrium state. As already explained, in this condition, the gravitational force and the spring force are equal in magnitude. The spring force itself can be determined from the spring constant d and the static displacement S0. After rearranging the equation, the displacement S0 can be calculated from the gravitational force and the spring constant as shown. For the oscillation, we now displace the sphere downward from this equilibrium state. As is usual in oscillation analysis, we describe the motion of the sphere relative to the static equilibrium state. Thus, the oscillation takes place in a coordinate system whose origin lies at the static equilibrium position and whose positive coordinate direction points downward. Let us now consider the oscillating sphere in the illustrated position. The restoring force acting in this state results from the difference between the downward acting gravitational force and the upward acting spring force. It is important to note that the gravitational force acts in the positive coordinate direction and therefore is assigned a positive sign, whereas the spring force acts in the negative coordinate direction and thus must be considered with a negative sign. In this way, we obtain the restoring force with the correct sign. If, as in this case, the gravitational force is smaller than the spring force, the restoring force will have a negative value because it points upward in the negative coordinate direction. Conversely, if the sphere is displaced in the negative coordinate direction, meaning that it is above the static rest position, the gravitational force becomes greater than the spring force, and the restoring force then has a positive value because it now acts downward in the positive coordinate direction. This correct treatment of the sign convention is of crucial importance because otherwise the differential equation would not have a valid solution. Let us now analyze the positively displaced sphere and the forces acting on it in more detail. While the gravitational force always acts constantly downward, the upward-directed spring force depends on the displacement s. The spring force can be determined using Hooke's law. However, it is essential to note that the elongation x in Hooke's law refers to the total extension of the spring compared to its unstressed state, and not only to the displacement from the equilibrium position. Therefore, the total elongation of the spring results from the sum of the static extension S0 and the dynamic displacement S from the equilibrium position. The previously derived formula can be used for the static extension S0. In this way, we obtain the given equation. We now expand the term in parentheses and thus obtain the shown relationship. In this equation, the spring constant is eliminated. The gravitational force terms cancel each other out. We can now see that for the vertical spring pendulum, the relationship between displacement and restoring force is exactly the same as for the horizontal spring pendulum. This relationship can also be clearly visualized in the force displacement diagram of the spring. The diagram shows the elongation of the spring from its unstressed state on the horizontal axis. When the sphere is attached, a static displacement S0 occurs first. This point on the spring characteristic curve then serves as a new coordinate origin from which the spring is described. In this shifted coordinate system, we once again obtain the same proportional relationship between the effective spring force and the displacement S. Attaching the sphere therefore merely shifts the equilibrium position in which the gravitational force is compensated. We can therefore disregard the gravitational force and determine the restoring spring force directly using Hooke's law. We therefore obtain the same relationship between restoring force and displacement. From this relationship, the same differential equation follows. For the sake of completeness, we derive it once more. First, we determine the acceleration of the sphere from the restoring force using the fundamental law of mechanics. In this resulting equation, both acceleration and displacement are functions of time, where the time dependence of the acceleration corresponds to the second time derivative of the displacement function. We now see that the same differential equation results as for the horizontal spring pendulum. Consequently, the solution of this differential equation in the form of the displacement function is the same. The vertical spring pendulum is therefore described by the same equations of motion as the horizontal spring oscillation. In particular, the oscillation frequency and the period result in exactly the same way. Therefore, it does not matter for the description of oscillating spring systems whether the spring oscillates vertically or horizontally. Note that the angular frequency omega can also be interpreted in connection with a circular motion whose projection represents the oscillation. If the angular velocity of a rotating disk is adjusted to the value equal to the square root of the spring constant divided by the mass, then the projection of this circular motion corresponds precisely to the motion of the oscillating spring. I hope you enjoyed the video. Don't forget to like, comment, and subscribe if you want to see more.